homework 14. We're jumping to chapter 7 just for a little bit, and then we're going to go back. But right now, I think is a good time to do stuff that's in chapter 7. Your homework is to read 7.1. That's page 385 through 390. Just read it. It's review of inverse functions, basically. Everything in there is just review, except for the last 2 pages, and it tells us how to deal with inverse functions in calculus. So for instance, if you have some function f, and you want to know, and you have an f inverse of x, and you want its derivative, there's a nifty formula in terms of f. But I'll tell you right now, the reason we're not dealing with this is because I have almost every theorem in this book memorized. Just because I've worked with this stuff for so long. The stuff in this section, I don't know. So it's not a big deal is what I'm getting at, right? But it is good to know. I do want you to see it. So just read it, and I suggest, as I always do, if you're reading something and there's a proof in it, just jot it down as you're reading it. Because it's good. It's good for you, right? To actually put pencil to paper when you see numbers and equations and stuff. So just do that. But it's mostly just a review of stuff you already know about inverse functions. Then then the actual assignment is from page 403, section 7.2, numbers 31 through 55 odd. Okay. So, what do you get for this?
A to the x plus y.
Yes, okay, so a to the x plus y. Right, and the way we could think about this is that addition goes over to multiplication, right? That's how we usually, that's I think how I said it when we first did this in Algebra 2, is that when you throw addition into the input of an exponent, right? The operation here is exponentiation, and when you throw addition in, it works out to be multiplication of the outputs. Okay, not that important, but we do want to make sure we have this for today. It will become important. Now what about this? A to the x, then raised to the y.
A to the x times y.
A to the x times y. And so another way of thinking about that is that multiplication in the exponent goes over to exponentiation. And it works both ways, right? It is reversible. This is the same thing as a to the y and then raised to the x, whatever. This is just stuff we're going to need for today, just briefly. But yeah, okay, so that's basically a quick review. Now, can you take a guess what we're going to do today? It has something to do with derivatives. We're going to be taking the derivative of some kind of function. Can you guess what kind of function it is? No guesses. No. Okay, all right, well here. Let's think about this. E, we have defined it previously as the limit as what does what? Do you remember? As n goes to infinity of 1 plus something. 1 over n. And then raised to the nth. Okay? That is how in Algebra 2 and over the summer we defined E. And we proved that this exists over the summer and stuff like that. And so, right? And the idea is as you make n really, 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 really large, yes, this gets really, really small, but this also gets really large and it has this nifty effect. It doesn't just work out to be 1 plus 0 raised to the infinity, right? Something interesting happens. And we know that this, as you make n larger and larger and larger, this thing gets closer and closer to this specific value, 2.718, 2818 to 8459045, and so on. It goes on and on and on, right? Yeah. And the bigger you make n, the more digits you get out of it, or rather, the closer that the digits get to the value. But anyway, okay. Here's my claim, and I think this was in a homework problem. In fact, I'm 100% sure I assigned this one. My claim. We're just going to check this out here. Is it true? But my claim is that this limit is exactly the same thing as this limit. the limit as h goes to 0 of 1 plus h raised to the 1 over h. Does that make sense? Let's think about it. So
Yes.
it does make sense, and I want to be very explicit here. I'm going to make a little table. There's n. Because we're thinking here, n is going to get larger and larger and larger. So n is eventually, as we make it bigger, it'll get up to 1. And then it'll get up to 10. And then eventually it'll get up to 100. And then it'll get up to 1,000, and so on and so on and so forth. Meanwhile, what's happening to 1 over n? Well, at first, it's just 1 over 1. And then it's a tenth. And then it's a hundredth. And then it's a thousandth. And we can think about, okay, well, what does h do as it drops down to 0? Well, it goes through smaller and smaller numbers too. In fact, we could say, okay, well, let's pretend that h is starting off at 1. As it gets closer to 0, it will eventually get to 1/10. And then as it gets closer to 0, it'll go through 100th. And then it'll get down to 1,000th, and so on and so forth. And then, meanwhile, 1 over h is doing 1 over 1, then 1 over 1 over 10, 1 over 1 over 10, which is the same thing as 1 times 10 over 1, which is just 10. And then 1 over 100, which is just 100. And then 1 over, and so on and so forth. And we could see that whenever 1 over n is, that's what h is, right? Those two match up. As you make that bigger, this gets really, really small. As you make that smaller, this gets really, really small. They go through the same values eventually. Ditto, as n gets really, really, really large, this exponent gets really, really, really large. And same thing here. As h gets really, really small, 1 over h gets really, really large. And so, like, if you were to just tabulate this, and for each one of these values, you did 1 plus, you just saw what these values were. Now, I don't know, I guess 1 would be 1 to the, would be 2, and then 10 would be whatever it works out to be. It's like 2.7, it's not, but we'll just pretend. And then eventually this would be 2.71, maybe 7, and then eventually 2.7182, and so on and so forth. Well, the same thing's going to happen as you go through your h's, right? 1 plus h. In fact, the way I've set it up here, you'll get the exact same values. This would go to 2. This would go to 2. When h is 1/10, this would be 2.7. With h is 1/100th, this would be 2.717, and so on and so forth. And so, with a limit, we only care what happens there at the end, when h actually gets to 0, or n actually gets to infinity. And we can see that they both go to the same place, right? They both converge to e. So, in fact, I could have, if I wanted to, when I first introduced e, I could have defined it this way. It's just nice with this way because it had something to do with compound interest, if you remember that, right? There was like, you had your interest rate over n, and the n was the number of compoundings and stuff like that. And so that's nice, but I could have just as easily defined it this way. They mean exactly the same thing. They have the exact same limit. So that's just something to know. Okay, so do you buy that?
Yes.
Okay, so from now on, this is e right here. That is what e is equal to. E is the limit, as h drops to 0, of that stuff right there. Okay, so, all right. And it's still 2.718281828459045, and those are the only digits I've memorized. So now, can you guess what function we want to take the derivative of today?
Log.
How about this one?
E to the x.
E to the x, the natural exponent, right? Or rather, I call it the exponential function. We'll get into that in just a second. But if we get the derivative of this thing, we're going to be able to get the derivative of a lot of things. And it turns out this thing is fundamental. I've been saying this for years. Like, the exponential function is one of, in a sense, it's one of the most fundamental functions. interestingly, because it's fundamental, right, what I mean by fundamental is like not just like that it's ground, like it's foundational in a sense. And we'll see that more and more as we work. But this function is central to calculus for this specific reason. And I'm about to show you. So let's take the derivative of f of x. By definition, that's the limit as what? The limit as, how about h?
H goes to 0.
Of, and let's, without the e to the x,
No.
just what would the definition of that be right there?
F
F
of
of,
x plus h
there you go, f of x plus h
minus f of x
minus f of x, just plain old difference quotient.
over x squared.
Over what? What's the definition of a derivative? You're in calculus. If this is f of x plus h, and this is f of x, then the height is equal to f of x plus h minus f of x, and then what's the run? What would this point have to be?
Oh, it's h.
Yeah, the run itself is h, but that point
X
is
minus
x
x.
plus h, and just plain old x, right? This is the idea of difference quotient, and so then the distance between it always works out to be h. You should be able to wake up from a dead sleep, and somebody puts a gun to your head and says, "What's the definition of a difference quotient?" Like this you should be able to spit this out at any given time. This is just by definition what the derivative is. And like in the quiz, yeah, there are different ways of writing it. Sometimes you want to do it like this. But then whatever goes down here, it's the same thing right there, right? And we take a limit as x goes to y or as y goes to x, whatever. But in general, well, I mean, it's perfectly general anyway. But this is probably the most easiest way of doing it. So, okay, so now you tell me what to write here, given that given that f is actually e to the x. So, f of x plus h is?
E to the x plus h
E to the x plus h
minus e to the x.
minus e to the x all over.
H.
Okay. Now, here's the thing. I'm looking at that, and I'm thinking, I don't know, I don't really see anything. So maybe we just rewrite something. I can't really rewrite that. I can't rewrite that. Can I rewrite this guy as something?
E to the x times e to the.
There you go. And again, I have no idea what I'm doing. I'm just saying, well, nothing's really coming to me. I'm not sure where to go from there. But I know that I could rewrite this as e to the x times e to the h. Okay. What can we do now?
You can split it up into multiple.
Split it up into what? Split what up?
Into multiple.
Oh, you mean like e to the x, e to the h minus e to the x over h? You mean like that?
Yes.
You could. You could. And we could work on that for a while. And we probably won't get anywhere with that. Especially since over here, and then we'd have the limit of this minus the limit of this, and we'd see that e to the x isn't moving as we move h, but h is. So you have x, because remember, like anytime we're doing this, we're imagining that we had some x, right? We have our function, and we want to know what is the derivative at this point. Maybe it's 2, right? And so over here you have e to the 2. And the idea is, well, and then you could go through and plug in actual values and stuff like that. But all we've done here is we said, well, I don't want it just at 2, I want it at x. But once you choose that x, that guy's not moving. Whatever that x happens to be, once you plug it in, he's stuck, right? And so as h moves, this guy's stuck. He's like, even if he's a really big number, like 100 million, right? You still have 100 million over h, or I guess a really small number. Whatever, 0.01 over 100 million. Eventually, h is going to get so small that that constant number is going to blow up. So this is not going to help us. So what's another thing we could do?
If you could factor out an h.
Can't factor out an h, but there is something we could factor out of this numerator right there.
X.
What?
Well,
Not x, because he's up. He's inside of e. It's not going to help us, because then, I mean, if we took a log in here, we'd have to take a log out here. I mean, I guess you could write something as log e log something, but that's just going to make stuff look uglier. What can we factor out? Look, let's say e to the x worked out to be 7. You'd have 7 times e to the h minus 7. Can you factor something out there?
7.
Yeah, so what can we factor out of that?
The e to the x.
The e to the x. Why am I doing this? I don't know. I mean, that's the only thing I can do, really. The only thing I see. I mean, or like you said, you could split it up. You could split it up. The nice thing about with limits, though, is if you could factor out something that is not moving as h goes to 0. Does this change at all when h changes?
No.
So it's constant as far as h is concerned, and so we can pull it out.
Yeah.
And why would we want to do that? Well, just to simplify what we have. I'm not sure what's going to happen here, but I'm going to pull out that e to the x because he's constant. And now I have a slightly less complicated thing. Everything has an h in it. I mean, except for 1 now. We have e to the h minus 1 over h. But now we have a limit without any x's in it, which is probably going to be easier. Probably. I don't know. But now I'm looking at this and I'm thinking, well, now what? I don't know. I mean, maybe, I mean, what you could do is graph it and see what happens, right? You could graph e to the h. Only, I mean, when you graph it, you'd probably graph it as x instead of h. But nonetheless, you could graph this and you'd see that it goes somewhere and you could guess that that's the limit. Or, and this is the key here, is you could say, well, hold up. This is e to the x times the limit as h goes to 0 of e raised to the h. Like that, like that. But e, remember what we just did, e is defined in terms of a limit. And not just any limit, but the limit as something goes to 0 of 1 plus h to the 1 over h. And so it's like, well, hold up then. Since this limit's going to 0, I want this value, maybe if I write this as something where this value in here gets closer and closer to e as h goes to 0, I could actually do that. I could say, instead of writing it as e to the h, I could just write e as this guy right there, because that h is indeed going to 0. Does that make sense? Yeah. And so I'm going to say, okay, well, this is the same thing. I would get the same thing, right? Like, and this is the idea, right? Is like, if you were doing this, you could just plug in a bunch of different values for h, right? Like, that's what a limit is. You're imagining as h gets closer and closer to 0, what does this do? And you could find that out. And you'd see that if you just replaced this with this, you'd get the same numbers. Same way as before, right? You had the limit going to infinity, and it's getting closer and closer to 2.7, blah, 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 blah. You rearrange it so that it's h, and then instead of 1 over n, it's h. Instead of n, it's 1 over h, and they go to the same place. Well, this right here will go to the same value as that right there.
Yeah.
And so now,
it's just 1 plus h to the 1.
Yeah, so let's check this out now. So now let's use our, so e to the x is a constant, he's going to stay there. And we're going to take the limit as h drops to 0 up. So what's my rules for exponents here? We multiply them. And so I have 1 plus h raised to the, let's see, that's 1 over h times h, which is what?
H over h.
Which is h over h, which is what?
1.
Always 1. So I'm not even going to write anything there, right? Because that h hits that h, they cancel out, and we just have that. I go minus 1 all over h.
So it's just...
Do I need those parentheses anymore?
No.
No, okay, so then what does the numerator work out to?
H.
Just h, so we have e to the x times the limit as h goes to 0 of h over h. What's h over h?
1.
It's just 1. So we have e to the x times the limit as h goes to 0 of the constant number 1. It's always 1, and therefore
It's just e to the x.
it's just e to the x. So this summer, I don't remember exactly what work you did, right? But I know when I was working on the proof that that limit converges, what I ended, or rather, you know, so if you remember, we had to try to show that this thing is less than the next one, right? We had to show that it was increasing. And so this is one of the things we wanted to do. And one thing when I was doing this was like, what I kept coming back to was like, damn it, this would be so easy if this were just one more, right? Like if I could just add one right here, or if I could make this one smaller, then it would be easy to prove, right? If I make that, or whatever, right? And then like you do a bunch of rearranging and you end up with some crazy expression, and it's always off by just one. It's like it's off by a hair, you know. If it were any smaller, I'd be able to do this. If this were any bigger, and it just. And it's interesting is that's kind of what's going on here too, is like, this is just right. It's just right so that this limit works out to be 1. If it were any bigger, it wouldn't be 1. If it were any smaller, it wouldn't be 1. But this interesting definition right here, the limit as h goes to 0 of that thing, is the thing which makes this right here work out to be exactly 1. In fact, you could define e to be the function which, when you take the derivative of it, it doesn't change. And that's what we've just found. We took the derivative of f, and what we got was, we got f right back. F prime of x is e to the x. It does not change. So what's the second derivative of e to the x? It's e to the x. It stays e to the x forever and ever and ever. No matter how many derivatives you take, it's always equal to itself. Now, just as an aside here. So earlier I said like that this function is fundamental in a way. It's like, I mean like foundational to stuff. Let's think of some foundational numbers. What are if I think of, you know, fundamental numbers, what pops into your head? Okay, but let's think way simpler. What's one of the first numbers you learn? 1. What's another one that's a lot like 1?
0.
0. And let's think about what properties they have. 1 is the number where you take any other number and multiply by it, and you get that original number back. 0 is the number where, when you add any other number to it, it stays the same. E to the x is the function where you take the derivative of it and it stays the same. These are like the building blocks of math right here, 1 and 0, right? Basically, you start with these two numbers and you build up from there. In a very similar way, E is foundational in a way. It's a little bit different, but when it comes to calculus, this is like the function, right? In this sense, like if I were teaching arithmetic right here, I would say like 1 is the number, and 0 is the number. Like it's where everything else is based off of these numbers here. E to the x is the same way, the function, the exponential function. Another way of writing this, d dx of e to the x is just e to the x, right? Okay, so let's think about what this means. The slope, right? So this is the slope of that function at some given value x. is equal to the output value of the function itself. So another way of saying this is like, so we have our function f of x, which is e to the x, and its slope at any given point. So let's say here at 0, what is the output value here?
1.
1. You plug in a 0 into there, you get e to the 0, which is just 1. But that's also what its slope is equal to there. And so its slope right here is 1. When you plug in a 1, you get out of e to the 1.
2.7.
Yeah, right. You get e to the 1, which is just e, or 2.7, whatever. It's just e. And its slope right there is equal to e. Plug in a negative 1, you get e to the negative 1, or 1 over e, and its slope is there as well. You kind of see, like, this function, the function which has this property has to have this shape right here. Right? Like, now it could be, it depends where you start though, right? Because, like, for instance, if I said there's some function where you plug it in and it gives you a negative 1 right there, okay, negative 1, and I say that its slope is equal to that, okay, well, I guess it would look like that. So then if I moved over this way some, it would go down some, and now it's even more negative, so its slope there is even more negative, and so it would have to come down like this. Move over here, its slope is less negative, and you could do the same kind of reasoning that it would have to look like that. So, interesting thing, interesting. It depends where, like, what one of those output values is. Well, we'll get there in just a second. We'll get there in just a second. So, what's going on here? Well, so, while this is the only function that does it, it's actually a member of a family of functions that has this property. So for instance, let's say that f of x is equal to 2 times e to the x. What's its derivative?
Just 2 times x.
2 times, and let's just do the derivative of e to the x. What's the derivative of e to the x?
E to the x.
2 times e to the x. So, oh, it's the same, right? So a constant doesn't change that.
Yeah.
Right? And so that's kind of how that works. So for instance, if my f of x were negative e to the x,
It'd still be negative.
it's still, right, f prime of x, it's still the same. It's still the original. It has not changed because that's just a constant right up front. And what that would do would say, well, we know negative e to the x looks like this, and it still has this property that its value at any given point is the derivative of that. Its slope at any given point is equal to the value at that point. So at negative 1, its slope is negative 1. At 1, or negative e, negative e to the 1, its slope would be negative e, and so on and so forth. But anyway, that's just something to know. Okay, all right, so all your homework is for this, well, for the most part, is just working with this. We're just going to take a bunch of functions, e to something, and take the derivative of them. Or the square root of something, something with e in it, right? Or sine of e to something, or e times e of something to times sine something. And so just you want to get familiar with that. So let's do just a few of these. Now, this is a little bit different. This isn't exactly the same. Let's take the derivative of this function. Okay. So
It'd be e to the x cubed.
nope. No. So the derivative. So remember. So this is e to something.
Yeah.
What's the derivative of e to something?
Just the same.
It's just e to whatever is in there, right? It's just whatever it is. Then we multiply by the derivative of the inside stuff. What's the derivative of 3x?
3.
Just 3. So that's e to the 3x times 3, or a nicer way of writing that is 3 e to the 3x. Right? That's just chain rule, right? Because you could even think about that as, well, let's say, well, f of g of x, where we have e to the g of x, like that. Where that g of x was my 3x, right? And you'd say, well, the derivative of this would be f prime of g of x times g prime of x. So in other words, the derivative of this is just that. So that is your f prime. But now you have to multiply by the derivative of the inside stuff. And that's all that's happened right here.
I was just saying you could rewrite it as e to the x, the entire thing cubed, right? And then take
Oh, yeah. Good. So let's see that, okay? So we could say from the beginning, f of x is the same thing as e to the x and then cubed. And so now we use a chain rule again. So the outside stuff would be the derivative. Let's say, bring that down, bring that up. So 3 squared. Yeah?
Yeah.
Multiply by the derivative of the inside stuff, which would be e to the x. And so we have 3 times e to the, so let's go ahead and use that again. That would be 2x, yeah? Times e to the x, which is the same thing as e to the 2x plus x, which is 3e to the 3x. So yeah, I see what you're saying. Cool. I was like, how did you get cubed? I was thinking you meant like this is somehow that jumps. I'm like, you're doing it backwards. No, the power jumps down. That doesn't jump up. Yeah, I got you. This is a little bit more complicated. And in general, and this is one of the reasons why I'm doing this right now instead of just letting you discover it as you do like 90 of these things, is that in general, like when you have anything like this, the derivative, you could think about it as the constant jumps down, and that's it.
Okay.
It's that easy. Now it gets a little bit more complicated when it's not just a simple constant times x. So for instance, okay, so you got all this, and so you could rewrite it in a creative way like you were thinking, and it would work just fine. It's just that chain rule usually is the most direct way of dealing with this. So let's just say e to the x squared right there. So now the derivative is, well, the derivative of e to the stuff is just e to the stuff. That doesn't change. Then we have to multiply by what?
E to the x. Derivative of.
The derivative of what?
E to the x.
No, we just did that. So I said the derivative of e to the stuff is e to the stuff.
Oh, x squared.
And now the derivative of the inside stuff. So in this case, right, the outside stuff is e to the stuff, right? And now we're working our way in, and so we take the derivative of that. So ex squared times 2x, or I like to write my e's at the very end of whatever I'm writing. And so, again, with exponential functions, really all you got to do when you're taking the derivative of them is leave whatever that is alone, and then just multiply. You could think about it as the derivative of this stuff drops down, right? And so, like, I guess symbolically here, if f of x is equal to e to the any function right there, then its derivative is, this always just works out to be whatever it is, and then you just multiply by whatever the derivative of that stuff is. So let's do a couple more, then we're going to get into something else. We'll do a bunch of examples. So, which one do I want to do? We did that. Let's combine these guys and say, okay, let's say we have a constant times e to some constant times x. What do we do?
2 times derivative of 3x.
Yeah, there you go. Right, derivative of 3x.
That's e to the 3x.
This guy stays the same.
So it's just 6 times.
6 e to the 3x is f prime. And so, yeah, right, because constants just come along for the ride. We take the derivative of the outside stuff. Yep, leave the inside stuff alone. Yep, and multiply it by the derivative of the inside stuff, which happens to be 3. 3 times 2 is 6, and we're done. All right, let's do slightly more complicated here. Okay, way more complicated, but here we go. So, f prime. What happens to the 2?
Stays.
Comes along for the ride. What happens to here?
Derivative of square root of x plus 1.
Yeah, okay, I see what you're saying. But yeah, and so, yeah, the derivative of e to the stuff is e to the stuff, so that doesn't change. Then, we take the derivative of this, which is what?
X 1/2 times x plus 1 to the negative 1/2 times 1 times, yeah,
Times 1, yep. That's something, you know, I didn't say this when we were doing implicit differentiation, but like, technically what you're doing, like if we take d dx of both sides, you're doing this and you are multiplying by the derivative of x with respect to x. It just happens to be that the derivative of x with respect to x is 1, and so we don't write it, but it is true. And so it is true that with the chain rule, as you do this, because what you've done here is you're taking the derivative of x plus 1 to the 1/2, and so you said bring down the 1/2, yes. Demote him down by 1, yes. Then multiply by the derivative of the inside stuff. And so you're absolutely 100% doing the right thing by saying multiply by the derivative of the inside stuff. It just turns out to be that the derivative of that is 1. And so we have 1/2 x plus 1 to the negative 1/2 times 1, which I'm going to go ahead and rewrite as 1 over 2 root x plus 1, like that. And so we have 1 over 2 root x plus 1. I guess we could cancel out those 2's, 2 in the numerator, 2 in the denominator, and rewrite that as e root x plus 1 all over root x plus 1. Okay, so you should have plenty of these to work with, get the feel of it. I'm going to go ahead and talk about another topic because it pops up here in the homework. And if you don't know what this means, you might sit there and go, wait, what are you talking about? You look through your book and everything. I just want to tell you what this is. A differential equation. A differential equation is any equation that involves derivatives of a function. So for instance, here's the differential equation. Y prime equals y. We're understanding that y is a function, right? We're not talking about a variable here. We're talking about y as a function. And this says that we're looking for the function that has this property, that when you take the derivative of it, it's equal to itself. So you could say, well, I know what that is. We just talked about it today. Y of x, I guess, must be e to the x. And you could double check that. Y prime is equal to e to the x. Is e to the x equal to e to the x? Yes, that's your solution to your differential equation. We're not going to get into this. And like I said earlier, it turns out that this one equation isn't unique here. In fact, infinitely many of these work. And it works with any constant times e to the x. Right? It's like we had 2 e to the x, we took the derivative of it, and we found, oh, it was 2 e to the x. Okay, so there's actually a family of functions for which this is true. Infinitely many, right? I could put any number in here. I guess 0 does work.
Yeah.
Because 0, what's the derivative of 0? Well, it's 0. Does 0 equal 0? Yeah, okay. And that's one of the things with differential equations. Oftentimes, 0 works, but it's called the trivial solution because it's trivial, right? And so any equation involving derivatives of a function is called a differential equation. And so you might have something with higher derivatives. You might have something where the second derivative of something plus its original is equal to 0. That's a differential equation. You might have a bunch of them. You might have something like, let's do one that we're actually going to do. Y plus y prime is equal to, where is it? Y double prime. And the thing is, so there's an entire branch of mathematics called differential equations, where people study differential equations. Last year, I wrote a differential equation up on the board. And it was, oh man, I'm never going to be able to remember it right. It's going to annoy me. It was like this, d sine dx plus dt equals v, or something like that, and I said, this is called the Schrodinger equation. It is not this. I've completely messed this up. There's an I in here somewhere, I don't know. But anyway, the idea is, and this is what's called a partial derivative, and therefore a partial differential equation, where the function is a function of multiple variables. And so when you have a function of multiple variables, you don't take the derivative of it with respect to t, you take the partial derivative of it with respect to t. Don't worry about this doesn't matter. But anyway, so when your function, here it's understood that your function is of one variable. And it could be anything. You call it t, you could call it u, you could call it x, whatever. When you have a function of multiple variables, you have to specify. Did you take the derivative with respect to x, or did you take the derivative with respect to time, etc.? And these things right here, everything, like, well, there's a quote, and I looked so hard to find the author of this quote, couldn't find it. But it goes, nature speaks to us via mathematics. Her language is differential equations. And so this is huge. This is a big thing, right? And this is like the first differential equation you learn. And it turns out that when you have stuff like this, it's kind of simple, right? I mean, it's certainly not a partial differential equation or something like that, but they get hard quick. They get hard real quick. And so if you go to college, you take about a year of calculus, and then you take one course, differential equations, and then another course would be in linear algebra. And you move on and do more stuff. But almost always you do differential equations after a year of calculus. And it's just, here's an equation, how do we solve it, right? So anyway, what was I going to say? We will talk, we're going to do a few differential equations in this class, but one of the things, because like I said, this function right here is so fundamental, a good guess for any one of these, because you have a thing, you have the function itself, and the derivative is in the equation. Maybe this thing looks like this. Or maybe it's not exactly e to the x, maybe it's some constant times e to the x. Or maybe it's some constant times e to the x times or e to the constant times x. And that's usually your first guess. Is you say, well, here's a function, and if I do some stuff, its derivatives show up and stuff like that. Maybe, just a guess here, that it looks something like this. And then the idea is, okay, well, how can I make this work? And so let's just see. Okay, so this question is a little bit different, but I would like to just go along with the thought process we have here. You're given some equation that involves a function and its derivatives, and now we're saying, well, since it involves its derivatives, maybe it has some form like this. I don't know. So let's just see what happens. Here's my original function. Y is equal to some constant, e to some constant times x. Now let's take its derivative, and what do I get?
It's c times k.
Yeah.
To the e times e to the
E
k.
to the kx. So then what's its second derivative?
C times k times e to the x.
K times k, or how about k squared? E to the kx. And you see, like, the more you start dealing with these, the more you start to see quick patterns, and you can just pick this stuff up real quick. And it's like, okay, well, is this true? Can we find a k or a c that makes this true? So let's just plug it in and see. We have y plus y prime, so we have c e to, I'll write it up here so you know exactly what I'm doing here. We have the differential equation, y plus y prime equals y double prime. Now, y is some constant e to the kx. Y prime is that constant times k. That constant times k e to the kx. And that's supposed to equal that constant k squared. Oops. That constant k squared e to the kx. And now, really, I guess c doesn't matter. That could have been a 5. Right? And it won't matter because I could just pull it out, right? Yeah. Like, I could say, well, let's pull out that c, and we have e to the kx plus k e to the kx equals c k squared e to the kx. So it doesn't matter what c I used. I could have used any c in the world, and this would still work, apparently. So I'm just going to cancel, divide both sides by c, as long as it's not 0. But again, if it's 0, then this function is just 0, and so its derivatives, and so obviously it works because 0 plus 0 is still 0. So that's a trivial solution. We don't care about it. Now let's see what we have. We have e to the kx plus k e to the kx equals k squared e to the kx. It looks like I could get rid of the e to the kx because he shows up every single place. And that's one of the cool things about this. Is whenever you have something like this, if you guess that it's e to the x, well, another thing, can we just divide by e to the kx? What's the only number we can't divide by?
0.
Is e to the kx ever equal to 0?
No.
No? Oh, that's nifty. Like, that's one of the nice things about this is that, well, you never need to worry about dividing by 0 because e to anything is never equal to 0. So I could just divide by it. And so now I have 1 plus k equals k squared. And so it depends. This will work for any c. And now, as long as k obeys this right here, and so let's see what that is. I'm going to rewrite this as 0 equals k squared minus k minus 1. Can we find out what k is equal to?
K minus 1 squared. So k is equal to 1. Wait, no, that doesn't work.
No.
Can you factor?
I don't think so. But k should equal 1 plus or minus the square root of 1 minus 4 times a times c makes it a positive, all over 2. And so we have 1 plus or minus root 5 over 2. So the golden ratio, that's kind of cool. So as long as k is equal to one of these, so it looks like we have infinitely many solutions because c could have been anything. But right now, we could say that if y is equal to any number times e to the 1 plus root 5 over 2x, or, so that's one solution, your other solution is going to be any number e to the 1 minus root 5 over 2 times x. And so we have these two solutions. Actually, infinitely many solutions, and you could go back and check this if you wanted to. In fact, let's just do that. Let's take one of them. Let's take C1 and say, okay, let's just make sure that it obeys this right here. In order to do that, I'm going to need to take some derivatives. So here's my function. Y equals some constant e to the 1 plus root 5 over 2x. Now let's take its first derivative, and what do we get?
C times 1 plus root 5 over 2 times e to the 1 plus root 5 over 2x.
X. Okay. Now let's take its next derivative, and what do we get?
C times 1 plus root 5 over 2 squared.
Yeah, because that one drops down, it's that times itself, and so it works out to be 1 root 5, 2 squared, e to the 1 plus root 5 over 2x. Now let's just plug it into here and see if it works. Y was that guy, so c e to the 1 plus root 5, 2x. Then add that to its first derivative, c 1 plus root 5 over 2 e to the 1 plus root 5 over 2x equals y double prime was this, so some constant times 1 plus root 5 over 2 squared times that thing, which is e1 plus root 5 over 2x. And I could see, okay, c shows up everywhere, so c didn't matter. It could have been any number in the world. If it were 0, it's obviously true, so let's assume it's not 0. I'm going to divide everybody through by c. Goodbye. I also see that e to anything, well, it shows up the same way every single time. I could factor it out, or I could go through and divide by each one of these. So I divide him out, and he's gone, he's gone, he's gone. What am I left over with? 1 plus root 5 over 2. Is that indeed equal to this? And it's like, well, yeah, that's what we did. Like, we basically had the equation 1 plus x equals x squared, and we solved for x. That's what it is. But let's just to really drive the point home, let's just do it. We're going to have, I'm going to write this, well, here, let's see what happens over here. So squaring that gives me a 4 here. First, outer, inner, last gives me 1.
5. Oh, no. 1 plus
2
root 5.
2 root 5.
Plus 5.
Plus 5. So that's 6 plus 2 root 5 over 4. This is the same thing. Now we need this to be over 4. Well, I want it to be over 4 here. So I'm going to change this. I'm going to multiply the top and the bottom by 2. And I'm going to multiply the top and the bottom by 4 here. So we have 4 over 4 plus this is over 4. The 2 jumps in, gives me a 2 plus 2 root 5.
Which is 6 plus 2.
Which is 6 plus 8. It works. Oh, lo and behold. And so these show up all the time in everything, especially physics. But differential equations of this form, this is called an ordinary differential equation. Because there's ordinary and there's partial. Ordinary is there's only one variable. That is, the function that you're trying to find has only one variable, and there's a bunch of derivatives going on. And you want to find out what it is. A good guess, a good place to start is, hey, maybe it looks like this. And then you go from there, and oh, lo and behold, it works. And then from there, you figure out, like, they're just, like, I could look at this, rearrange it, and give you the answer in a couple seconds, because that's just what you do. You generalize it, right? You say, oh, if a differential equation can be written like this, cy equals 0, if you could take your differential equation and rewrite it in this form, then its solution has this specific form. And that's one of the reasons I hated differential equations, because it was what I called a toolbox class. where it was basically just like an algorithm. Like, if your differential equation looks like this, turn it into this, and here's your solution. If it looks like this, turn it into this, and here's your solution. There wasn't much theory behind it, besides what I just put up on the board, which is, hey, look, it works. All right, cool. And honestly, that's how many the solutions to many differential equations were found. Was that there's another quote. As I was looking for this quote, I found a different quote, which was like, it said something like, the way to solve different, and this is like, you know, a world-renowned mathematician, I forget his name, who said, the way differential equations are solved is you stare at it until you have an idea of what the solution might look like. And that's how it works. Okay, so real quick, let's do a hard one. So you're going to have ones that are, oh yeah, see, that's why I wanted to do that one. I didn't give you one that's that hard. You're going to have one that'll say, show that this is a solution to the differential equation. This and to show that something's a solution to the differential equation, you just, well, let's see, we have y, okay, so I'll just plug that in. We have a y, well, we'll just take a derivative of this and find out what y prime is. We'll take its second derivative and find that. Then you just plug everything in and verify that, yes, it does work out. So that's one of your homework problems. I'm not going to do it for you, but that's the idea there. The one that we just found that with the one that we had, which was y plus y prime is equal to y double prime, that the solutions have this form, 1 plus or minus root 5 over 2x. Your book gives you this, or this will be like what it has. It'll give you this, and it'll say, find the values of lambda for which y equals e to the lambda x is a solution to this. And so what it's saying is, and you might not know what it means, but it's just what we did. We said, okay, well, the derivative would be lambda e to the lambda x. Second derivative would be new lambda squared comes out, e to the lambda x. And you can see how these are very similar to quadratic equations, right? Because if you have a constant up here, every time you take a derivative, you get a new one of these guys. And so they're very much related. And you could say, okay, to find that, it's exactly what we just did. E to the lambda x plus lambda e to the lambda x equals lambda squared e to the lambda x. You could cancel these guys and you get 1 plus lambda equals lambda squared, so that lambda is equal to 1 plus or minus the square root of 5 over 2, because you do all the stuff because you recognize, oh, that's a quadratic equation. No wonder we spent so much time on this for years. Like, it shows up, like, and these are actually like real things like this. Anyway, okay, so how much time do we have? We're a little over. Let's just do one example. So you'll have 2 or 3 on these. 1, 2. Oh yeah, I did want to do this. So yeah, I wanted to make that up. So we don't need to do those. Let's do one like this. Find the equation of the tangent line to this curve. X e to the y plus y e to the x equals 1. Find the equation to the tangent line at the point 0, 1. And I can see that if I plug in a 0 for x, I get a 0. Plug in a 1 for y, I get a 1 times e to the 0. 1 times e to the 0 is 1 times 1, which is indeed equal to 1. So yes, that point is on that curve. Now, we want an m, which we could think of as a y prime of x, or a dy dx. And so, what do we need to do to this bad boy?
Subtract x.
Not going to happen. Not going to help you.
Do implicit.
Say again?
Implicit differential.
Yes, exactly. We're going to take the derivative with respect to x of both sides. So, in other words, everything from now on is going to build on everything we've done before now. And so this would give you a 0. And now, okay, so this is a product. Take the derivative with respect to x, he stays put. Then add that to, leave that guy alone, take the derivative with respect to x of this. We get e to the y times y prime. Now, the derivative of this with respect to x. You follow me on that?
Yes.
Okay, so derivative with this, we get y prime, leave the second thing alone. Add that to, leave the first thing alone, take the derivative of the second thing. Now we get all our y primes on one side, everybody else on the other. And so I have my y prime x e to the y, that's that guy, I just rewrote him, plus y prime e to the x right there, equals negative y e to the x minus e to the y. Pulling out the y prime and then dividing would leave me with x e to the y plus e to the x. Did I do that right?
Yes.
Right, because I pulled out the y, that was left there, that was left there. Now I plug in my 0 and my 1. I get negative 1 minus e to the 1, which is just e. 0 is gone, yeah, and that's a 1. So how about negative 1 plus e? I could leave it as minus 1 minus e, that's fine. But that should be my slope at the point that I care about. Minus 1 plus e. And so get ready for, like in this section, your values are going to have e in them. Like when you plug something in, your output value is going to have an e in it. Get used to that for the rest of your life, because that's how most things look like from now on, really. Like, okay, so we have some kind of crazy curve, okay, and here at 0, 1, we found that its derivative is negative 1 plus e, okay, so we want a y equals mx plus b. We know that m is equal to this. And when I plug in a 0, I get out a 1. So I plug in a 0. I get out a 1. 0 makes this whole thing go to 0. I get 1 equals b. Therefore, the equation that I'm looking for is negative 1 plus e x plus 1. Right there. So your stuff's going to have e's in it, and it could easily have been the case that when you plugged this in, you had something involving e here for b. Don't be afraid of that. That's what it should look like. And there you go.